Okay, I'd like to welcome everyone to this distinguished lecture series. This is the J. William Urick, Anastasia Vernest Distinguished Lecture Series. And today we're very honored to have Dr. Paul Bevilaqua give this lecture. Dr. Bevilaqua was at Lockheed Martin Corporation, and he worked for Skunk Works. He's an expert on VSTOL. And for aerospace engineering, VSTOL is extremely important, and so we're really honored to have him give us this short course. So with that, I introduce Dr. Bevilaqua.
Well, thank you very much for coming to the lecture. I'd like to talk a little bit about the problem of designing VSTOL aircraft. There's a lot of utility for them. They can be used as ferrying workers out to the offshore oil platforms. They actually start getting paid very good money when they get on the helicopters today, and it takes them a long time to fly out there at 100 knots, and they're not producing anything. Executives like to be able to fly from where they are to where they're going without having to go through a helicopter to the airport and change to a bizjet, then another helicopter. Tourism. People like to explore rough sites, Galapagos Islands, where there may not be developed airfields. Police, of course, use helicopters today, but they're slow. There's a need for air ambulances all over the country, really, or especially in rural areas where people are far from hospitals. And of course, there's new interest now in package express for drone deliveries, power line service. You're flying over the power lines. Right now, you have to report the problem. Somebody has to come out in a truck to fix it. If you could land and fix it, that would be great. And of course, firefighting. You'd like to be able to put people down where they need to be, and if they get in trouble, be able to pull them right out again. Another need is for the crowding that are going on in airports. People don't want to increase the number of airports, increase the size of their runways. So there would be a need to get some of the big airplanes off the runways. Most of the regional jets go less than 600 miles, 65% of them out of Chicago, 60% out of Atlanta. And those regional jets take as much time in the queue and to take off and land as the large intercontinental and long-range jets. So if you could get them off onto taxiways, you wouldn't have to enlarge the airport, but you could increase the throughput. The military, of course, would profit. Most third world countries have one major airport in the capital, and the large transport airplanes will need access to that airport, which means the fighter aircraft are going to have to operate from wherever. And if they could be VSTOL, it would be a huge advantage. And in fact, the Air Force is interested in perhaps buying some of the VSTOL versions of the F-35. The Marines rely on the Harrier now. They're an expeditionary force, which means they go ashore without artillery support. And they need top cover, and they need artillery support, so they use the Harrier, which comes ashore with them on the beach, to provide that kind of close air support without having to rely on the carriers being offshore. Another rescue mission that people are interested in performing was, an example was the Iran hostage rescue mission back in 1980. The Iranian students captured our embassy employees and were holding them in the embassy as hostages. We wanted to go in and rescue them. And the thought was, if you could get a C-130 to land in a soccer field, you could get in and out and rescue the hostages. So Lockheed looked at taking JATO rockets, adding them to the airplane, so that as it slowed down and you didn't have enough wing lift anymore, you turn on the rockets that would allow you to land, and then you'd fire retro rockets to slow you down within the length of the airfield, soccer field, and then use JATO to take off again in a short length. Pretty complicated system. They were testing it. They made several successful takeoffs and landings, but the pilots hit the retro rockets too soon in one case. They weren't on the ground yet. It made a hard landing, destroyed the airplane, and they decided it was just too risky to try to rescue the hostages that way. So they attempted with a combination of helicopters and C-130s in the desert, and they ran into a dust storm, ran into each other, killed some of the rescuers, and so the whole mission was aborted. They would really like something that would be able to perform this mission. So with all those needs, there have been a lot of attempts to build a VSTOL airplane. I call this the wheel of misfortune. There are around 50 airplanes on there classified according to the lift concept in an attempt to get VSTOL capability. There are only really two truly successful VSTOL airplanes, the Harrier and now the F-35V Stovall strike fighter. So what are the lessons from the wheel and the history of the VSTOL efforts? Well, after World War II, rockets were a new technology, taking off vertically, and fighters had thrust-to-weight ratios close to 1, so they thought it would be simple enough to increase the thrust-to-weight ratio of the fighters a little bit, put them on their tail, and take off vertically. That ran into a lot of problems with limitations on vertical lift, inability to take advantage of a runway if there was one available, and pilots couldn't land because they couldn't see over their shoulders. So the second generation up here kept the airplane horizontal but installed lift engines in the fuselage to give you vertical lift and kept a cruise engine in the tail for a cruise flight. And that ran into a new set of problems. First of all, the lift engines on the CG were where you wanted fuel and payload, and they were hot, so the hot gases would hit on the ground, impinge back on the airplane, blow out the tires, melt the aluminum skins, and if they got re-ingested by the lift engines, cause them to stall with a loss of lift. Plus, the lift engines were dead weight in hover, and the cruise engines were dead weight in hover, and the lift engines were dead weight in cruise. So in the third generation, up here, they decided to use the same engines for lift and cruise, and they vectored the engines. That solved one of the problems of dead weight and engines on this in the CG, but they ran into the same hot gas ingestion problems. So the first successful VSTOL airplane was the Harrier, which used a single cruise engine with thrust vectoring nozzles. So the history is kind of, first we tilted the airplane, then we tilted the engines, then we vectored the engines, and finally realized all we had to vector was the nozzles. Well, with all this need, and there's some airplanes out there that seem to work, why aren't there more VSTOL airplanes? Well, one issue is that large aircraft are difficult to hover. If you take a helicopter, for example, which is simple to visualize, and it has a thrust-to-weight ratio of around 1, it actually needs to be a little greater than 1, but around 1, and you take those blueprints and you double every dimension and build another identical helicopter just twice as big. Well, the thrust is proportional to the area of the rotors, pi r squared. So r squared, if you double it, it's 4 times the thrust. But the weight is proportional to the length times the width times the height. So it's L cubed. You'll have 8 times the weight, and so you'll have half the thrust-to-weight ratio of an identical smaller helicopter. And that's the problem that nature deals with. Hummingbirds are the largest animal that can hover. If you get to be a little bit bigger bird, you need actually a running takeoff. And if you watch geese and ducks taking off, they jump out of the water, they run on the water with their wings to take weight off their legs, and eventually are able to take off when they reach flying speed in ground effect. Eagles, which are even bigger, can't use that technique, so they nest high up on treetops or on cliffs and jump out and dive down until they reach flying speed, and then they climb away. American Indians, you know, they wear those feather headdresses. They didn't need to catch and kill an eagle in order to get the feathers. They would stake a rabbit to the ground and then put a buffalo robe fence around the rabbit. An eagle would swoop down, snatch the rabbit, and then get jerked out of the air. And he wasn't able to take off, so they could just walk into the enclosure, pluck the feathers they needed, and then let him out, and with enough of a running start, he could take off. So here's the equation that determines the thrust-to-weight ratio that you need to take off. So it's proportional to the aerodynamic drag, it's proportional to the rolling resistance, the friction, and it's proportional to the lift you can develop on the wings, which is basically 1.44 comes from a factor of safety that is mandated. 1.2 times V stall is your takeoff speed. And then the wing loading, you want a big wing for lots of lift, and the lift coefficient. You want a high lift coefficient. So here are some curves as a function of the WS over C sub L. So large C sub L and large C sub S are good. And what you see is that it's not good enough. You get down around 1,000 feet and nothing you can do will give you enough lift to take off in anything less than 1,000 feet. You basically have a thrust to weight ratio big enough to take off vertically, so you have a vertical takeoff airplane. Now that's not to say if you only have 300 feet available, you won't use it, because the wing has a thrust to weight ratio or lift to drag ratio on a fighter of about 10, on a transport airplane around 20. So if you can get just a little speed over the wing, that helps you a lot in getting off in a short distance, carrying more payload and fuel. So we classify VSTOL aircraft according to their takeoff distance. A conventional takeoff and landing aircraft takes off in 5,000 to 10,000 feet and uses mechanical flaps to get a lift coefficient of about 2. Then a short takeoff airplane takes off in 2,000 to 5,000 feet. It uses powered lift, boundary layer control, thrust vectoring to get lift coefficients of 4 to 6. An extreme STOL airplane takes off in 1,000 to 2,000 feet. It needs powered lift coefficients around 6 to 8, plus reaction controls, because it'll be flying so slowly that the aerodynamic controls aren't enough to keep it under control, and so it needs reaction controls. And as I said, you've effectively got a vertical takeoff airplane, which is defined as anything from 0 to 1,000 feet, which requires the thrust to weight ratio greater than 1 plus the reaction controls. So you may have heard that VSTOL airplanes are no good, they've got no range. A VSTOL bomber can't bomb the end of its own runway, but that's comparing apples to oranges. If we compare an F-16, which is the dark colored strip here, to a Harrier, which is the light colored strip here, and they're both operating from an 8,000 foot runway, the Harrier has essentially the same range payload performance as the F-16. If the runway reduces to 4,000 feet, the F-16 has to offload fuel or payload to get off, and it only can go 100 miles, whereas the Harrier still has the same range payload performance. If you cut it down to 2,000 feet, the F-16 can't take off at all. The Harrier has the same range payload performance as it did from 8,000 feet. If you go to 0 takeoff, okay, then the Harrier does have limited range payload performance. But it's not fair to compare a Harrier forced to take off at 0 feet to a conventional airplane that can take off in 8,000 feet. So, what are some of the lessons we've learned from that wheel of misfortune? You need to keep it simple. You can't rely on aerodynamic controls. You need reaction controls. You need more thrust to take off vertically than you do to take off or cruise conventionally. You really ought to use thrust vectoring. If there's any runway available, 200-300 feet, use it, because the wing is such an efficient thrust augmentation device. You don't want hot, high-energy jets. You want low-energy jets. And you want lift improvement devices to get as much lift as you can out of the airframe. So let's talk about the main subject, propulsion. Propulsion drives VSTOL aircraft design. Here's some pictures of various airplanes from the wheel of misfortune with various kinds of propulsion concepts that have been explored. Tilt rotors, tilt wings, tail sitters, thrust vectoring, ducted fans, lift fans, ejectors, and lift engines. I'm going to talk about some of those and what lessons we've learned from them. Here's a comparison of the thrust required for a transport aircraft compared to the thrust required for a vertical landing, assuming you can take off in a short distance or from a conventional runway. So depending on the requirement, you can get by with a thrust to weight ratio of around 0.25 to maybe 0.3. So here's maximum speed at 35,000 feet. Here's maximum speed at sea level. Here's climb after takeoff, acceleration at sea level, 40,000 foot ceiling, and all of them get you within 3/10 or so thrust to weight ratio if you have a big enough wing. Here's what's required for a 1,000 foot takeoff as a function of the wing loading, and here's what's required for a vertical landing. So when you're coming back for a vertical landing, the assumption is you've burned off enough fuel that you're lighter than when you took off, and you don't need quite the thrust to weight ratio that you did to take off. Here's the same analysis for a fighter aircraft, and you think, okay, with enough high speed requirements, enough maneuver requirements, you might be able to force the engine large enough to get vertical as a fallout. So here's wing loading and thrust to weight ratio again. Here's sustained G. So to get a small, cheap, affordable engine, you want a very big wing. But to go very fast, you want a very small wing to get a small engine. So the compromise is somewhere around here, which is not enough thrust to reach the 1.2 criteria that you would like to get a VTOL airplane. So that's why you need some sort of thrust augmentation, why it's a little easier for a fighter than a transport airplane. And this kind of summarizes it. Here's the percent of thrust you use in cruise as a percent of the thrust required for a vertical takeoff. So as I say, for a vertical takeoff aircraft, you want thrust to weight ratio around 1. A fighter is close to that already, so it doesn't need much of a boost to become vertical. A strike fighter is even less than that, and a subsonic transport needs a huge boost in order to have enough thrust to take off vertically. So it's in the 2/10 to 3/10 range and needs to get out to 1.2 to be vertical. So what do you do to get more thrust out of an engine? Well, thrust is the product of mass flow and velocity. So you can get more thrust by opening the valve and getting more flow through your hose, or by getting higher speed. So let's compare those two approaches. If you increase the mass flow, call that capital M dot V, or you can increase the jet velocity, call that M dot capital V. If you look at the ratio of those two approaches, it's inversely proportional to the velocity ratio. So we want to compare thrust per horsepower. For a given engine with a given horsepower, what's the best way to get thrust out of it? Increasing the mass flow or increasing the velocity? So you turn thrust into horsepower by multiplying by the relevant velocities. You want them to be equal. So you solve that equation for the velocity ratio, substitute it back in here, and look at the ratio at the bottom. And it turns out that you get more thrust per horsepower by putting your energy, your power, into a large mass flow of air at a low velocity than you do putting into a small mass flow of air at a large velocity. So helicopters are much better at hovering than rockets. And this is a classic plot showing that on a scale. Here's thrust to horsepower and disk loading, which is basically how big is the rotor area compared to the thrust you're developing. And helicopters are up here, 6 to 8. Propellers are down here. Disk loading is around 100. Lift fans are 250, 300, and pure turbofan engines out around 400 or 500. So the thrust to horsepower out here is only around 2, whereas the thrust to horsepower for a helicopter can be 6 to 8. So let's take a look at rotors. Here is a device producing vertical lift. It's an actuator disc, which means it has infinite number of blades and infinite porosity. So it doesn't exist, it just puts a pure force on the flow. So the thrust is the force delta P times the area of the rotor. And as it turns out, if you run through the math, the velocity going through the rotor is half the ultimate velocity in the far field, and the area shrinks down to half the area. So thrust is mass times velocity, power is thrust times velocity, so mass times velocity cubed, and thrust per horsepower is proportional to 1 over V. So again, you want a low velocity and high mass flow to get good thrust per horsepower. Here's what's happening. The flow accelerates from 0 at infinity to the half velocity at the rotor face, and the pressure drops according to Bernoulli's equation, it accelerates. Then you apply the force, you actually have higher pressure underneath than you do above, but obviously the mass flow is continuous, so there's no change in the mass flow. And then the flow has to relax back to atmospheric pressure, which causes a vena contracta that gives you a smaller area and a higher velocity. So the thrust is still delta PA. In terms of mass flow and velocity, it's 2 rho v squared A, power is 2 rho v cubed A, thrust to horsepower is 1 over velocity as before. Now the interesting thing is you can get the same thrust from a ducted rotor with a smaller diameter. So what happens in that case is the flow accelerates to a lower pressure in the duct, jumps up to atmospheric pressure within the duct, and so it comes out at that lower, smaller area, higher velocity directly from the duct. The horsepower is 2 delta P times half the area. In this case, I've said the rotor is half the area. So horsepower is rho v cubed, thrust is rho v squared, thrust per horsepower is 1 over v. And they fall on that same curve I showed you before. It's just that the duct gets you more, how do I want to say it? For the same thrust, you need more horsepower because you've got a smaller area, higher velocity. But it's smaller in diameter. Also, if you're talking about a drone, say an unmanned drone making helicopter deliveries in your front yard, you don't want an open rotor at neck height swirling around. Some guy's going to run up to get his package and get his head chopped off. So you perhaps want to shield it with a duct. The disadvantage is to transition from hover to flight, you can tilt a rotor and it works fine. The duct now has a high angle of attack. There's separation from the leading edges, and so it's difficult to transition the ducted rotor to forward flight. Here's a side-by-side comparison. So the ultimate velocity and areas are the same, but the rotor is twice the diameter in this case, and the duct is half the diameter of the rotor, and more power required. Here's a map, a fan map, to help you design a fan. So on this axis here, we've got the fan diameter, and on this axis here, we've got the horsepower. So if you're at this point and you want more power, one obvious way to do it is what your intuition tells you. You put more power into it. So you go from 1,000 horsepower to 1,200 to 1,400 to 1,600, keeping the fan diameter the same. And so you're getting more power, but more thrust, but you're putting more power in. Another way to do it that isn't as intuitive but works pretty well is to increase the diameter of the rotor. So you keep your 1,000 horsepower engine. You don't need a bigger engine making more power. You need a bigger fan or bigger rotor. And as you increase the diameter of the rotor, you get more thrust per horsepower out of it. So depending on what your airplane is, whether you can make the engine bigger or the fan bigger, you can move up that curve either way. You can use that as a design chart to get you into the right ballpark. Okay, if we look again back to that wheel of misfortune, I told you that they basically went through tilting the aircraft to vectoring the thrust, and there were 3 basic schemes: jet schemes, rotor schemes, and ejector schemes. So I'm going to talk about each of those and their advantages and disadvantages. The first ones were vertical takeoff, and then they tried again when the jet engine came along. They thought the thrust to weight ratio of a jet engine might make the concept more attractive again. So what happens when what should an aircraft weigh? Generally speaking, 1/3 payload, 1/3 fuel, 1/3 airframe structure, with the airframe structure including the propulsion system. With the VSTOL airplane, we saw we needed more engine, more thrust to weight, bigger engine, lift fans, whatever. So you've got more weight in the propulsion system, and that either comes out of fuel or payload. So you either get decreased range, or to keep the range the same, you can't carry as much stuff as far. There's another disadvantage of oversizing the engine. Here's the specific fuel consumption. Pounds of fuel per pound of thrust. versus the thrust, and engines are very highly optimized to operate at cruise at maximum efficiency. But if you have a big engine, you have to throttle back when you get into cruise, and so your fuel consumption gets up. So even though theoretically you've got a good thrust to weight ratio with your engine, you have to carry more fuel. And the lift system, then fuel plus engine, may not be all that efficient as you think from the propulsion engine point of view. The other lesson from tail sitters is you need to take a short takeoff. If there's any runway available, you want to use it. Get some lift on the wing to help you take off, lift more fuel, more payload. So you really want to be able to use a short takeoff. And with a tail sitter, you had no choice but to take off vertically, very limited in range payload. And you want to size the engine for the mission, not the fuel. And if you can count on some short takeoff to offload the thrust required, you can then put in a smaller engine better matched to the cruise requirements. Physically, the pilots were able to take off vertically and transition over to cruise. Their problem was landing. The theory was that you come in, you slow down, as lift comes off the wing, you're going to vector the airplane so that a component of the propeller thrust cancels it. You move the throttle forward, you're working your alpha and your throttle together and try to keep the airplane horizontal and then settle down. Well, no pilot wanted to sink, so he left a little speed and ended up doing a zoom climb to scrub off the last of the kinetic energy, turn it into potential energy, but now he's hanging upside down. He can't see over his shoulder where the ship is. He's got no vertical descent velocity indicator. He doesn't know how fast he's coming down. And in fact, Kelly Johnson flew an airplane like that. The pilot said, practice landing on clouds. He said, this is not a good idea. And Kelly gave the money back to the Navy and said, let's not do this anymore. We're wasting your money. So the main lesson is, this is a really, really bad idea. Although I should say, if you have an unmanned drone with no pilot in it, and you're content to go short ranges, it might be worth thinking about for package delivery. So one concept that attempted to fix the problem was to keep the airplane horizontal and put fans in the wings. And I'm going to talk about this airplane later, so I won't go into a lot of detail now. It went through transition problems as well. When it was trying to land, come in to slow down, it could pitch up and vector some of the thrust forward, develop lift at high angles of attack, and come to a hover stop. But to go forward, it needed to vector some of the thrust aft, so it tilted nose down, now started to move forward to develop lift on the wing, but the wing's at a negative angle of attack. So when he got up to enough speed, he had to quickly flip up and hope that he could develop enough wing lift before he fell out of the sky. So I'll go into a little more detail on that, but it turned out not to be a very good idea. The other alternative was to put some sort of lift system in the fuselage, and the Germans and the French and Lockheed looked at various lift systems, including lift engines. So the advantage of a lift engine is it's got a short life. It only runs for maybe a minute on a 1-hour mission, say a fighter or transport aircraft. So it doesn't need to have the life of a 2,000, 3,000 hour engine. So you can overtemp it and burn it up slowly. So the very first lift engines had high thrust to weight ratios because they were very hot. But as I mentioned, now the hot gases would re-ingest, splash up on the airplane, melt the aluminum, burst the tires, get ingested, stall the lift engines. So as they moved on in progress, instead of going up in thrust to weight ratios, they came down as they made the jets cooler and they switched to a turbofan system. The other problem with lift engines is if you've got, say, a thrust of 1 and half of it comes from a lift engine and half of it comes from the cruise engine during conversion, you're at 71% of your total thrust. You've lost 29% of your thrust by splitting it. If you have a thrust of T and you vector it at 45 degrees, you get 70% for acceleration, 70% for lift. You don't really lose any thrust. You start very efficient. So there's a fundamental 30% loss in lift with the split system, lift engines plus a cruise engine. So what are some of the lessons from that generation? Cruise engines are dead weight in hover, lift engines are dead weight in cruise. They occupy volume for fuel and payload on the CG where you want those disposables. You need to carry fuel for the whole mission and then burn it at the end so that the effective thrust to weight ratio of a lift engine is not what the engine company quotes, but what you have to carry plus the fuel. You need 2 mechanics, 2 sets of manuals, 2 supply chains, 2 sets of tools, 2 thrust stands. You need too much support equipment when you have 2 different engines. They are not magic anti-gravity devices. That's the first thing most people think of. I'll just stick a lift engine in and I've got a magic anti-gravity device. Propulsion interactions require you to really look at aero-propulsion integration. Other problems. Well, you've got an airplane with air coming in the top, going down through the lift engine, and coming out the bottom. So you put a moment on the slipstream, so there's an equal and opposite reaction in the airplane, which causes the airplane to pitch up. So you've turned the flow down, and so the airplane pitches up. So you want to use thrust vectoring, not split flow, because of that 30% loss. The hot lift jets cause tires to burst, fountains buckles the skins, stalls the lift engines, and you really want to increase thrust with mass flow, not with velocity, with a high temperature lift engine. The Russians specialized in lift engines, and they actually ended up having to coat the underside of their airplanes with ceramic foam like the space shuttle tiles to keep the engines from melting the airplane. The lift cruise engines were an attempt to get a little bit better. They had a lift engine still, but now they put vectoring nozzles on the cruise engine to supplement the lift engine. So it's a step in the right direction, but it still had all the problems associated with lift engines and hasn't been successful. The Harrier has been successful. It has a single lift cruise engine. Same engine for cruise as you have for lift, and you vector the thrust efficiently. The problem with the Harrier, though, is that it's working the large disc loading. The Harrier has 20,000 pounds of thrust because it has that large fan, but it's only Mach 0.85. The F-104 Starfighter, which was designed around the same time, only has 15,000 pounds of thrust, but it can reach Mach 2. Because as you go supersonic, the skin friction drag comes down. You're at high speed, so your angle of attack is low, your induced drag is low, but the wave drag comes way up. And to minimize wave drag, you want to be long and slender, like a missile or an F-104. And if you've stuffed a helicopter or a large lift fan into your airplane, like the Harrier, you're too wide, you can't be long and slender to be a supersonic airplane. The British in the 1980s tried to get the Harrier to go supersonic by adding afterburners to the front nozzles, which were fan flow only, both in hover and in supersonic dash. But it was not working. I mean, you had all the problems with hot gas ingestion, plus the hot gases running along the fuselage melted the fuselage, and they ran into all of those problems. This is the Russian pure lift cruise design, like the Harrier, but they required 2 engines with 11,000 pounds of thrust each, and each had 1 rotating nozzle. The problem with multi-engine VSTOL aircraft, there's a higher probability of failure in hover. If you have 2 engines, you're twice as likely to have an engine fail in hover. And if you have an engine fail in hover, you've now got an asymmetric roll moment, because you have thrust on one side, nothing on the other side. The airplane will roll over. Even if you have ejection seats for a single seat fighter, it rolls so fast, the ejection seat will eject the pilot into the ground. What the Soviets did was they took a central planning approach. They put strings on the legs and arms of the pilot, and if the roll sensors that sensed that the airplane was rolling over. They pulled the pilot's legs and arms into the seat and ejected him before he could react, because pilot couldn't react fast enough to throw himself out. And that's where they ran into problems with the pilots being ejected into the ground. They're more expensive than singles. You have twice as many engines to buy and twice as much life cycle costs. They're heavier than singles, and they're not really that much safer. When one engine blows, it generally will take out the other engine. And then, of course, a single is on the CG, so it has relatively small roll inertias. Two twins are like a dumbbell, and they have a lot of roll inertia. So on the one hand, they argue it's safer because it's harder to upset the airplane and get it to roll. On the other hand, once it starts rolling, it takes a lot more force to get it stopped and bring it back. This is Boeing's concept for the Joint Strike Fighter competition. It was basically similar to the Russian concept, except they had one engine with two nozzles rather than two engines with one nozzle apiece. Okay, let's look at thrust vectoring, which is so fundamental now to the successful VSTOL airplanes. Here's what you find in most textbooks. There's an engine, there's a control volume around it, and they go through some analysis and say that the net force on the airplane is the difference between the incoming velocity and the outgoing velocity. So thrust is m dot delta v, and there's a thrust of 20,000 pounds. However, there's actually two very real forces acting on the airplane. There's gross thrust and ram drag. So in the case I showed you before, there would be 30,000 pounds of gross thrust and 10,000 pounds of ram drag for a net thrust of 20,000 pounds. But when you vector, you get 30,000 pounds of lift out of the engine, but you get 10,000 pounds of drag. So the Harrier pilots will go to an Air Force base and make a bar bet. I bet we can go up tomorrow in a red flag exercise. I'll let you get on my 6, and in 1 minute I'll have you in my gun sights. And the Air Force pilot says, there's nobody that good. You can't. I'll take that bet. So they go up there, and the Harrier pilot vectors his nozzle down. He gets a lot of lift, and he gets a lot of ram drag. So he stops in the air and pops up. The other guy flies over him. He comes back down, got him in his gun sights, and wins the bar bet. It's a great maneuver for bar bets, but the other guy has a wingman, and you're now stopped in the air, and a grape, and so you win the bar bet, but you lose your life. So it's never used in combat, but the Marines love to win bar bets with it. Okay, thrust vectoring nozzle. The simplest nozzle is a elbow. What happens is you get a force on this side that forces the flow to turn, and so it has to go from the high pressure here down to a low pressure and then back, and so there's an adverse gradient in a very short distance, and it causes a separation. Also, the flow tries to adjust, so it goes from low pressure to high pressure, sets up swirl, and those swirl motions don't contribute to the thrust, but they absorb some of the energy that you're trying to convert from pressure, hot high pressure gas, to thrust. So there are two sources of losses in a typical elbow nozzle: friction separation and resulting separation, and the secondary swirl passage vortices. Here's what the efficiency of a elbow nozzle looks like as a function of the bend angle. So you start out around 100% efficiency. By 90 degrees, you haven't lost that much. You're 97, 98%. But as you come below that, vectoring forward to help slow you down, you lose a lot more thrust, up as much as 10% if you vector fully forward. Here's the effect of pressure ratio. If you decrease the pressure ratio of the engine, that improves the thrust to horsepower because you're getting more like a lift helicopter and less like a jet engine. But it increases the nozzle losses. So here's a low pressure ratio engine supplying the nozzle, and as you raise the pressure ratio of the engine, you're getting more nozzle efficiency and less nozzle efficiency, more engine efficiency. This is the 3-bearing nozzle, which was an attempt to make a single nozzle that vectors up and down from cruise to hover, and it uses bearings that rotates like a piece of duct hardware you'll find in Home Depot, and that's where the idea came from, basically. Here's the efficiency of a elbow nozzle. This is the first segment is 30 degrees of vectoring, the second segment is 60, then 2070, 1080, and 090. And you can see that the most efficient way to vector the flow is to take a small angle first and then a large angle. And so you end up with 95 to 93% efficiency. So to solve that problem, people said, well, if the flow is separating on that short inner radius, what if we did all the turning with the outer radius and had no inner radius? So we just have ambient air there. It forces a larger pressure difference on the upper surface, but you've got a long radius. So it's more gradual and the flow can stay attached. And here's some data for a vectoring nozzle. Here's a rectangular vectoring nozzle, vented nozzle they call them. So as you change the length of the nozzle versus the diameter of the turn, you get efficiencies around 96%. Here's a circular nozzle. Here's a pure rectangular nozzle. Here's that pure circular elbow nozzle. So you pick up a lot of efficiency as you open up the lower surface. Basically, you're acting like a spoon or a snowplow. You turn the flow on one side rather than through a channel with passage vortices and separations on the inner surface. So here are some of the kinds of nozzles that people have looked at. This is the Harrier nozzle for the Aviate-A, Aviate-B. Here's that 3-bearing nozzle. Here's a nozzle with a deflector hood. Here's a nozzle that was designed for a supersonic airplane that folded into the fuselage to stow it for clean lines and supersonic flow. Here's another concept, block and turn nozzle. Here's a nozzle with a hole in the bottom with vanes that vector the flow through. So basically 3 concepts. 1, some sort of vectoring scheme from 0 to 90 degrees. Some sort of block and divert scheme. So you're either going out the cruise nozzle or down the lift nozzle, and then some nozzle that allows you to modulate the flow, split it between them. This is the best system, nominally highest efficiency at every angle. Here you can get high efficiency when you're going all out the cruise nozzle and high efficiency when you're going all out the lift nozzle, and there's nothing in between. It's terrible in between. And this nozzle attempts to fix it, so you get some penalty in between, but not as bad as this. Inlets are the other end of it. A lift engine basically needs flow through the engine to get started. You can't start a lift engine if it's not spinning. So on takeoff, they typically have a cartridge which blows and fires and gets the engine spinning, gets some air through it, they start the engine. When they're coming in for a landing, they put up a ramp, inlet door to divert some of the flow through the engine and get it started. The problem is, here's that scoop intake. It gets you high efficiency when you've got some forward speed, but when you're in hover, the door blocks the flow into the fan. It's like it's a blocker in front of the fan, so there's separations and a lot of losses. So they've tried to put doors into the door, and that brings the efficiency up some. But the really best system is a flush rectangular inlet, wide open, high efficiency in hover. This curve continues on up as you reduce the speed even further, and it has low distortion. Okay, so let's talk now about how you design a VSTOL airplane. It's hard enough to design an airplane. If you have a wing planform decision to make, you can have a delta wing, a straight wing, an aft swept wing, or a forward swept wing. wing position, you can have a low wing, a high wing, or a mid wing. For horizontal stabilizers, you can have a pure flying wing, you can have a wing body tail, wing body canard, or a three-surface airplane. You can put your vertical stabilizer, a single one on the center line, two on the wingtips, or use thrust vectoring. Inlet locations, you can have a lower inlet, an upper inlet, a nose inlet, or side inlets. So let's say you've got your lift system. It's a Harrier type lift cruise nozzle engine. You now have your fuselage defined. You've got some payload, you've got a pilot, you've got the engine. You need to make a choice out of the 4 choices for a wing platform. And then given your wing platform, you've got to make a choice out of the 4 choices for a horizontal stabilizer, and then a choice for the inlets. If you try to optimize your airplane by looking at all the alternatives, it's an impossible matrix. You can't do enough analysis to do it. So you have to use some prior experience. That's hard enough. Here's what happens when you go to a VTOL airplane. You have all the problems of the configuration, the airframe, but now you have to decide what kind of lift system you're using and what kind of posts you're using. 1 post, 2 posts, 3 posts, 4 posts, or some other configuration. So the matrix is huge, and you really need to study history, understand what works and what doesn't work, and hope you come up with a good idea. So let's look at laying out a VTOL airplane. Here's a wing canard. So you start out knowing where the center of lift is for your wing canard configuration, and you locate your engine so that the thrust post, in this case, it looks like there's a Harrier type fan up front here and a vectoring nozzle at the rear. So you locate your engine so that the airplane balances in hover based on the CG in the center of lift of the wing. Then you add the cockpit, the inlets, the fuselage, and locate the pilot's cruise station. Then you add vertical tails and assign location-dependent masses. So the fuel needs to be in the wing. The radar wants to be in front. The controls and displays have to be in the cockpit. Stores want to be on the CG. Landing gear needs to be oriented, if you have a tricycle gear, around that CG. And then any unbalance you try to take care of by taking the bodies, the items that don't depend on being in a particular location. So avionics service centers, APUs, etc., you locate somewhere else. McDonnell Douglas in the old days typically put a boom, single boom out the back of the airplane to put in all the equipment to balance out the airplane. The problem now is that you took your shot at it, but you missed it. The CG doesn't correspond with the center of thrust. So here's the initial center of thrust, here's the initial CG location, so you have to move the propulsion system in the airplane forward to match the CG location. When you move the engine forward, you move the engine and nozzle forward, you move the inlet ducts forward, you move the lift system forward, you move the AMAT and accessory drives forward. If you move the CG aft, the wing and control surfaces move aft, the main landing gear move aft, the fuel system moves aft, stores move aft, so you have to tweak it. And typically you're going to end up farther forward than you assumed when you just had a basic first cut at your design. And here are 2 airplanes that look pretty similar. Lockheed published this picture first. The Soviets always say they have the same problem, so they come up with the same solutions. That's why their shuttle looked like our shuttle, their Concordsky looked like our Concorde. But it does look a lot like the Lockheed airplane. Okay, so some truisms of VTOL aircraft design. You have to balance in hover. You need a thrust to weight greater than 1. 1.25 would be ideal. 1.1 is kind of a minimum. The Harrier has 1.05. So it was a widow maker until they had computer controls that could balance it a lot quicker and easier than the pilot could. 1 pound of thrust allows you to add 0.83 pounds of hover weight, so 1 divided by 1.2. you can never get enough thrust forward, and you can never get the CG far enough aft. Another problem is that weight growth will occur. And that's a two-edged sword. If you say weight growth will occur, it will occur. You'll say, all right, I expected 5% weight growth. I'm at 5% weight growth. I'm done. If you say there's going to be no weight growth, then you work harder until you get no weight growth. On the Harrier, the first engines had, let me see if I have a chart there. No. The first engines had around 16,000 pounds of thrust. So the Marines had to decide, okay, I can't afford to carry a Harrier, radar. I can't afford chaff and flares. And I have to take the engine out every 300 hours to service it because I have to overtemp it to get enough thrust. So they took delivery of the airplane. It didn't have all the capabilities they'd like, but it was vertical and it would go ashore and drop bombs. So Rolls-Royce went to work on the engine. They said, okay, we've got better turbine blades. We've got better materials. We've now got 2,000 hours of life out of the engine. And the Marines said, well, we've kind of gotten used to changing the engine out every 300 hours. Supposing we overtemp it a bit and keep changing the engine out in 300 hours, could we get enough thrust to include a radar? And they said, yeah, okay, give us a radar, we'll burn the engine up in 300 hours. So they got a radar on the next version of the Harrier. Rolls-Royce went back to work on the engines. They got the life back up again with better single crystal blades. They said, okay, now we got 2,000 hours on your engine. And the Marine said, well, if we ran it at 300 hours and overtemped it and burned it up, could we get enough thrust to support flares and chaff? And they said, yeah. So that's what they did. So they had a strict limit. There was no way they could put more weight on the airplane than they could lift. Turned out on our Joint Strike Fighter, if you remember from the fan map, same engine, you just make the fan bigger and you can get more weight on the airplane. So somebody came up with an idea, said, well, I could put this on the airplane. They said, yeah, we'll make the fan bigger. So if you look at the difference now between the the F-35B and the A and the C, it looks to me like a Humpty back camel because it's got a bump for a bigger lift fan. They've added 2 or 3 inches to the diameter of the lift fan, but if you've ever bored out an engine, you know adding at the circumference adds a lot of volume. So they got quite a bit bigger engine, lift fan, and they had no constraints, so they got everything on the airplane that they wanted on it. Okay, when you're designing the airplane, you can either choose a good propulsion system and then have some problems with ground environment, or you can have a good ground environment and have problems with the packaging of the propulsion system. Because of the square cube law, fighter aircraft larger than the F-18 are generally impractical. The ground effects get worse. You got more thrust coming down on the ground. The square cube law limits the size of the airplane, and you get so big that now control becomes a problem. If you get much over 50,000 pounds, you actually have to end up like the V-22 with your lift engines out on the wingtips to provide enough control power. You can't do it with bleed air anymore. You don't want to use high compressor bleed from your engine because you pumped all that energy into it and then you don't burn any fuel and you don't exhaust it back out through the cruise nozzle. So you're doing a lot of work and you're not getting much payoff because at high pressure bleed, you've got a small mass flow of air at a high velocity. And they did that to keep the duct sizes small. You're transferring the power with pressure rather than velocity. But now you've got a small mass flow of air at a high velocity, which is inefficient. And you have put a lot of effort in our airplane designs to get the drag down. And now you're trying to decelerate. So you get slow to come to a hover stop, and aero drag goes away, ram drag goes away. And those are big factors at 150, 200 knots that help you slow down. So you don't have any aero drag. So you typically want to pitch the airplane nose up to get some thrust vectored forward. And that's a bad idea. The pilot can't see where he's going anymore. So you really want to be able to vector your nozzles 10 or 20 degrees forward of 90 degrees to help you decelerate. Okay, let's look at ground effects. Here's a picture of a Harrier landing in a dusty field, and you can see what happens. The jets hit the ground, they splash into each other, and they create a fountain. There's two effects going on here. One is lift loss. So if you're in free air, the jets move away from the airplane, and you get about a 5% lift loss due to the air being entrained by the jets and sucked down over the airplane. When you get into ground effect, those jets that used to be far away are now brought close to the airplane. And so you get much larger suck down, up to a 30% lift loss. That can be good if you're landing on a slippery carrier deck at night. You want to be down and positively sucked down. But if you try to take off, that's a bad thing. So you'd like to be able to control it. The other problem is with the V-22, you've got the jet slipstream coming down over the wings, and that produces a huge separation and suck down on the wings that limits the lift you're getting out of the rotors. So some people have said the next generation ought to have a tilt wing on it, but there were tilt wing airplanes on the Wheel of Misfortune, and their problem is as you start to transition to forward flight, you got a wing at 90 degrees angle of attack. It's a barn door. It's stalled till you get down to 10 or 12 degrees. You're not developing much lift, so you pick your poison. Okay, let's look at where that 5% lift loss comes from. It's pretty obvious where the suck down comes from. It's a force on the fuselage. But what happens to the jets? So here's the flow field induced outside of a jet. This jet is coming from the third dimension somewhere, so it's just a pure jet. It's sucking air in. Because the jet is getting weaker as it goes downstream, these stream tubes get further and further apart. If you stick a fuselage in there, you've got a stagnation point up here with high pressure. You've got air being rapidly sucked into the jet down here, so it's low pressure, and that creates opposite of wing lift. It creates suck down onto the airplane. And the question is, all right, so I've got a force on the airplane. Where is the equal and opposite reaction? According to Newton's law, if the jet is inducing a force on the airplane, the airplane should be inducing a force on the jet. So let's consider the jet to be replaced mathematically by a line of sinks, like a hole in a bathtub, drawing air into it. And look at the interaction between one sink and the fuselage. So you probably haven't had potential flow theory yet, but you can represent a body in a free stream with an array of sinks that give it some thickness. And a force on a sink in the fuselage is the strength of the sink in the fuselage times the velocity induced by the sink in the jet. So the force is the velocity of the jet is the Q of the jet divided by 2 pi s, the distance between the jet sink and the vortex and the sink in the fuselage. So the force is QF Q jet over 2 pi s. If you look at the other side of it, the sink in the fuselage is inducing a velocity at the sink in the jet, which is Q jet UF. UF is Q fuselage over 2 pi s. So the force on the jet is Q jet QF, just the reverse, 2 pi s. They're equal and opposite forces. So there's a pressure force being induced on the jet that reduces its thrust. And we had a computational model of the flow out of a cylinder. We took a wedge to represent an axisymmetric flow and calculated the pressures in the field. And what you see is that if the pressure of atmosphere is 2116.4, the pressure in the nozzle exit is actually above atmospheric pressure. So the jet is exhausting into a high pressure region. So let's look at that. What happens to a jet entraining fluid in a high pressure region? So here's a region where the pressure is higher than atmospheric and the flow is being entrained into it. And then we'll look at the flow after mixing coming out of the high pressure region into the low pressure region. So here's the entrained flow in the axial component. Here's the jet flow. And the entrained flow is U infinity times the pressure difference between P infinity and the high pressure region in the jet. And the jet velocity exhausts from the total pressure to the local high pressure outside the nozzle. The two streams then mix and momentum is conserved. So the mixed flow velocity after mixing is given by this sum of the momentums in the previous unmixed flows. So now we want to say this mixed flow comes out of this high pressure region into the low pressure region back to some U infinity, and we can use Bernoulli's equation to calculate what that velocity is when it gets back to atmospheric pressure, and then look at the ratio of the momentum of the mixed flow when it's back into the free stream to what you would have gotten if you just had the jet exhausting into atmospheric pressure originally. Here's that ratio. So you got the jet mass flow, the entrained mass flow, and the mixed velocity at the end over what would have happened if you'd ejected the jet mass flow directly into atmosphere. And that's the equation. Pi is the ratio of the pressures between P and P infinity. M is the ratio of mass flows between the entrained mass flow and the jet. And P and U is the velocity ratio. So if delta P equals 0, this term goes out, that term goes out, that term goes out. R turns out to be equal to 1 and the jet thrust is conserved. So a jet in free stream, thrust is conserved. If there's no entrainment, then R also equals 1. This term drops out, that term drops out, that term drops out, and the jet thrust is conserved. But if P is greater than P infinity, then R is less than 1, and so the jet thrust is reduced. If U infinity is 0, then the whole equation simplifies to this. The thrust is reduced by 1/2 mp squared. It's proportional to how much mass flows entrained and the square of the pressure difference. So the more the pressure difference, the more mass flow you entrain, the less thrust you get in the jet, the more suck down you have. Typically about 5% in free air. Where does the energy go? It goes into turbulence production. So this shows the velocities, and you can see that they're coming down this way and then they turn. And so by turning, they create this high pressure region inside the jet. The colors show the turbulence intensity, so you get a lot of turbulent mixing between the slow free stream out here and the high-speed jet with some turbulence production. If you use a thin-walled pipe, which doesn't have any flow directed towards the jet, then there's a lot less turbulence production, a lot less thrust loss, which is kind of physical, right? If you're coming out of a flat plate, you're going to get a lot of suck down. If you've got a thin-walled pipe, no flat plate, you're not going to get much suck down. And that's what the CFD shows. So what about ground effects now? You're getting close to the ground and you've got a 30% potential lift loss. What does it look like? Well, here's two jets impinging. They create a radial wall jet, which runs together and splashes up in the form of a fountain. On the center line between the two jets, it's straight up and it bends over because basically it's a radial jet just folded in the vertical direction. Here's what it looks like on a ground plane. So these are oil streaks. They put little dots of oil on the ground, then put a model airplane over it, turn it on. So here's where the two jets are, and you can see these radial wall jets coming out. They come together here and they cause this fountain that comes up on the airplane that gives it a boost. So what happens? You come down on ground effect without any lift improvement devices, and you get this huge suck down. If you put lift improvement devices on, you get enough of a boost that you cancel it. Lift improvement devices are shown here. Whoop. I'm sorry, where's the picture? There they are. You capture that fountain coming up from the ground and you turn it around and you throw it back down. So you get another boost from the lift, not just the thrust of the fountain, but you double it by throwing it back down. And that's what happens. So you can deploy your lift improvements devices on takeoff to minimize suck down and leave them undeployed on landing to maximize the suck down when you want to stick to the ground. Temperature is the other problem. When the gases from the fountain come up onto your airplane, they do cause a lift loss. So you're talking about a temperature of 1500 degrees Fahrenheit, say. So a 25-degree temperature rise in the engine inlet isn't much, but it causes a 7% thrust loss. So you have to consider your post arrangements. Here's the arrangement on our Joint Strike Fighter. There's a cold fan post up in the front and a hot aft post. So they come together, they create a fountain that runs across the lateral fountain with longitudinal jets. Here is the Boeing configuration. It has two lateral posts, which creates a longitudinal jet. This one has low hot gas ingestion because the cold post blocks the hot gases from coming forward, but the fountain only acts across the fuselage, so you don't get much of a lift boost. This configuration gives you low suck down because the fountain acts along the whole length of the fuselage, but now some of that hot air is going back into the engine and you have high hot gas ingestion. So if you look at this configuration, you can say they were really worried about lift. They wanted as much boost as they could get, and this configuration wasn't as concerned about it. Here's the Harrier configuration: 2 lift posts in the front, 2 lift posts in the back. They get a nice suck down fountain because they get one going longitudinally, one going laterally, but some of the hot gases are going to bleed forward and get into the inlet, so they had problems with hot gas ingestion. They never make a true vertical landing. They make what's called a rolling vertical landing. They move forward slowly, just fast enough to keep this hot gas from getting back up into the engine. Here's another alternative: 1 cold post up front, 2 hot posts in the back. That should get you low hot gas ingestion and low suck down. We didn't use that for other reasons having to do with aeropropulsion integration. So here's what it looks like on the ground. There's a modest pressure, 35 knot wind, modest temperature coming out of the hot post at the rear. There's substantial pressure because there's actually more thrust in the lift fan than there is in the hot nozzle, but it's cool. And then here's where that fountain comes and sprays out to the sides. So there's quiet zone here. You come through here, you feel a strong wind, and you come out here and there's no wind. Generally, they say stay outside 50 feet from the airplane and you won't get knocked over, you won't get burned up by the hot gases. So here's a cartoon showing what's happening there. You've got the lift jet coming down, creating the radial wall jet, which meets the radial wall jet from the rear post. They come together, they create this fountain that acts on the fuselage, and if some of it gets into the inlet, you get sucked down, and you can get a boost, which you can augment with lift improvement devices by turning the fountain back down again, as on the Harrier. Here's our experimental model being tested out at NASA Langley. And here's a guy showing that he's looking for that outflow. So you can see that there's smoke flow coming out, but he's standing there in the jet. And if you look closely at his legs, you can see his pants down around his shoes are being affected, but he's standing there okay. Basically, if you walk up to the airplane, I've done that, it feels like you're in a fast-moving stream. There's air rushing over your feet and your ankles, but your body doesn't really feel anything. So you have to kind of force your legs forward to walk up to the airplane, but it's not enough of a force to knock you over, because a low pressure over your whole body would knock you over, but a thin, high-pressure jet just feels like you're wading through a fast-moving stream. Here's what the pressure fluctuations look like. So these are pressure taps giving you pressure amplitude fluctuations. And you can see here where the fountain hits, you've got a lot of vibration and less so outside of that fountain impingement zone. These acoustic loads are important. You have to design the structure to take those acoustic loads due to the fountain impinging on the bottom of the airplane. Here's a CFD calculation showing a visualization of what's going on. Because the moment arm to the lift fan is shorter than the moment arm to the rear nozzle, you actually need more thrust in the lift fan than you do in the rear nozzle. So 48% in the lift fan, 43% in the rear nozzle, and almost 10% in the roll jets. So we call it a 2+2 configuration. There's two main lift jets that are large and two little roll control jets that are not so large. And here you can see what's happening. The radial wall jet runs back and runs into the jet from the hot nozzle and is deflected upward and kept from moving, keeping the hot jets from coming forward. Here's an IR picture illustrating what's happened. So white is hot. You can see the hot jet coming out of the rear post, and there's a cool jet coming out of the lift fan, but you can't see it, but it's there, and it curves back up. They interact and block it. You can see as the airplane comes down, there's like a wall created by the cold lift jet, which keeps the hot gases from coming into the airplane. The interesting thing is it doesn't matter how much the disc loading is. What's important is the thrust. So here's a downwash below 25,000 pound VTOL vehicles with jet lift, fan lift, helicopters, and here's the velocity at 100 feet. The differences have washed out. You basically have a situation like this. A rotor with 25,000 pounds of lift is the light blue. It hits the ground and runs out this way. A ducted fan with 25,000 pounds of lift is initially a lot smaller, but it runs out the same. So it's the thrust that determines what the radial wall jets look like, not what the lift system is. Okay, let's look at hover thrust budget. You've got an engine available. It's got a nominal uninstalled thrust, but you can't design for the nominal engine. You've got to design for the worst engine you're going to get. You have to take off hover decrements for suck down, heave, control power, hot gas ingestion, so you have less thrust than that available for your vertical takeoff thrust. The weight of the airplane has vehicle structure, subsystems, propulsion, operating equipment, so you have your operating weight empty, you add payload and the fuel you need in reserve when you land, and that gives you your maximum landing weight. And you need to have the thrust available greater than the vertical takeoff weight. There's that whole question of margin, whether you should include it or not. Typically airplanes grow 6%, but you really can't afford that on a VTOL airplane. There was a concern with these airplanes, the Joint Strike Fighter, that they are twice as big as the Harrier. Would they create problems landing on concrete and the aluminum pads that the Marines use on the beach? So we did a multi-physics calculation of a jet impinging on a concrete runway. So the physics for the heat transfer and the physics for the jet were the multi-physics. Concrete spalls at 1,000 degrees. The chemical bonds come apart and it becomes rocks and pebbles. So we ran the calculation and showed that when you land, you don't heat the concrete above 600 degrees. It spalls at 1,000 degrees, so you're safe. Unfortunately, we then said, okay, this is not a problem. So when Pratt went to build the first test engine, they built two nozzles. One nozzle to vector straight back to represent the cruise configuration, and one nozzle vectored down to represent the hover configuration. They tested fine with the cruise configuration, then they put on the hover nozzle, and they ran for more than 10 seconds. So the concrete spalled. They threw great chunks of concrete out in the employee parking lots, smashed windshields, dented cars up, and they realized you have to turn the nozzle upside down and blow up if you're going to run for more than 10 seconds. So it's a case where you're worried about a problem, you do some analysis, you think you don't have a problem anymore, and you forget about it. but then you change your boundary conditions and you've got a problem again. Here are the landing criteria. The thrust to weight ratio for one engine out. So if you have two engines and you lose one engine, the Army spec is 43 feet per second. They've tested helicopters in crashes and found that the gear collapse, the structure collapses, and at 43 feet per second, the pilot and co-pilot only break their backs. And that's deemed to be acceptable. So that's the design criteria for helicopter. Here's a typical landing velocity for parachutes. So people who land in parachutes know how to roll to absorb the energy, and they can survive that. But what is the requirement? If you lose engine out, say at a 50-foot hover height, to come down in this region, you need a thrust-to-weight ratio of 0.95. You really can't afford to lose an engine in hover. So we have ejection seats for the fighters. If you lose an engine, the pilot's going to go out. And this is just to remind you that wings are great thrust augmenters. You put some lift on the wing with a short takeoff. You augment that with proper placement of the nozzles, and you can get less thrust required for short vertical takeoff. That's the end of this lecture, and what I'm going to tease you with is aeropropulsion integration. Here's a wing with a jet blowing down from the trailing edge at 90 degrees. It's moving forward at some speed v, so the jet eventually is bent back in the direction of the free stream. And the question is, which way does the thrust act? Is it vertical or horizontal? Because if you do a control volume, the jet's coming out this way, so it should be horizontal, but you've ejected it this way and it should be vertical. It acts in both directions, and I'm going to show you next lecture why. Thanks for coming. Are there any questions? Yeah.
Yeah, so for the lift improvement devices,
Yeah.
that you mentioned, on the graph they had an improvement for 0 to 10 feet. Then around 20 feet it actually had a negative effect compared to no lift improvement devices.
Okay, that's a good eye. I didn't notice that.
Do you know why that would be?
No, I can't. I can only guess. Maybe all of the jet isn't contained within the lids. Some of it is on the outside, and when you get closer, all of the jet is now turned around, whereas originally some of it bled around the side.
Sure. And then you mentioned also having to turn the nozzle upside down.
Yeah.
For this. Can you elaborate on that?
Well, if the jet impinged on the concrete, it spalled the concrete because it heated above 1,000 degrees. So you have to turn it upside down so that the jet doesn't impinge on the concrete. So you simulate hover by blowing up instead of down.
Gotcha.
Because you need to run for more than 10 seconds.
Yeah.
Okay, if no questions, thanks a lot for coming. I appreciate your sticking with it and being here. Oh, another question. Yeah.
Also, for the duct versus the rotor setup,
Mm-hmm.
for the air wall between them, so obviously when it first exits the duct, the duct has a much smaller diameter
Mm-hmm.
for the airflow. But then they end up the same
Far away there.
far away. So if you had them close together, like on an airframe,
Mm-hmm.
would there be a difference, or they fall, or is there enough separation that?
Yeah, there would probably be some difference because the V-22, for example, has large rotors. They're hardly separated. They're less than the diameter of a rotor apart. So they would be thick and create a thick fountain. Whereas if a high-speed jet, like on the Harrier or the Joint Strike Fighter, are far enough apart and a lot faster, they would run together as thin wall jets and create a more concentrated fountain.
Thanks.
Okay.